OK, so it updates, the backend updates a heuristic. It will coalesce chunks. It attempts to safely link in the chunk into the list. Let's see how the front end does things, be it that it's not just a bunch of linked lists. OK, first thing that happens, it's going to get the chunk header. It usually does this by subtracting 8. But if certain flags are set, it will actually subtract more from that value. This is what Ben Hawks explained in his 2008 paper, and I have a kind of a contrived example in the exploitation section of this paper of how you could leverage this to gain code execution. The subsegment for this chunk is acquired. Again, it's not passed. It's calculated via certain values in the heap and the low fragmentation heap and the address of the chunk that you're freeing. By the way, that was really confusing when reversing this stuff because you had a bunch of weird arithmetic and a bunch of bitwise operations. It took me a while to figure out. OK, so now we've reached this point where we have this subsegment again, right? And we want to free to it. Again, the first thing you do, get that depth and get that offset. What you want to do is the offset to the next chunk that was stored in the interlock sequence structure, we're going to store it in the first 2 bytes of the chunk that we're freeing, because that will point to the next free one after we allocate this one. The depth, real easy. You add 1. You've just given a chunk back to the memory manager. If all goes well, it returns. I've left out a lot of code to show what happens, say, when you've freed every chunk in a user block. My paper explains it a little bit more, but it is confusing, and I just left it out for brevity's reason. OK, we'll continue with our Dr. Raid late night pizza thief example now. At this point, this guy has just taken a 3rd piece of pizza, and no one else has gotten one. You see what happened. The depth decremented again. The free entry offset points to 14. That's the next free slice of pizza we can use. Well, Dr. Raid, in all his slyness, realizes that first chunk, first piece of pizza he grabbed, it's ice cold. He doesn't want it. So what's he going to do? He's going to put it back in the box. And this updates our entries again. The free entry offset now points to 2. That is the first chunk. That is the first piece of pizza that was grabbed. The next offset in that chunk points to the previous free entry offset. See how the free entry offset here at the bottom is 14? You've just freed a chunk. The next entry offset is what was previously in that interlock sequence structure. Again, he's munching on that nice warm slice, 3rd piece of pizza, doesn't want the second one, and he puts it back. It's updated again. The free entry offset now points to 8. The depth has been incremented, and all those chunks are back. I like to think of this actually as a stack, right? So it's last in, first out. If we were to allocate memory, we would get that chunk. If we were to allocate again, we would get that chunk. So the first piece of memory you put in is going to be the last one you get out. And I think in the tactics section, it'll explain more of why this could be useful to you as well. On to security mechanisms. Everyone, I think, is kind of familiar with heap randomization, right? ASLR is prevalent. What they try to do is they will create a pseudo-random value that's 64K aligned, and they will add it to the heap base. That's so the heap isn't at attempts to make sure the heap isn't at the same address on every iteration. Be it that there's only 5 bits of entropy, I'm not saying it's impossible to guess that address. It is improbable. But if you have more than one attempt to guess the address, I think it could actually be doable, which I'll talk about in the exploitation section. We've seen some header encoding and decoding already. This made predictably overriding the size and the flags and the checksum nearly impossible if you didn't have an address link to figure out what values were used to XOR encode this stuff. There was a few things that I noticed. The first one I've already talked about. There's 4 bytes of this chunk header that have never been encoded. So if you could play around with those values, you could potentially leverage your way into an advantageous situation. The second being, you see how it does or ensures the encode flag mask is non-null. This encode flag mask is set in the heap create function, but theoretically, you could null it out. And if you null it out, that means this heap will no longer do encoding or decoding. The only problem with this is if you do this to a heap that has already been encoding chunks, the sizes of these things and the checksum will be all munged because they were already encoded, and if it treats as unencoded, they're going to be way off. Maybe you could create a new heap with this value and then do your size overwrites, but again, those are a lot of prerequisites. What did Matt Miller told me when I was writing this paper, you're laying the train tracks, you're not driving the train. I'm too stupid to drive the train, so I'll just lay the tracks, and hopefully everyone else can figure out how to get the train down them. Lastly, for this one, you see that the header is ANDed with encode flag masks. That ensures that this chunk that you're getting was at once encoded. But if you can overwrite the encoded 4 bytes of encoded information and make sure that returns false, it won't decode the chunk. It will treat it as an unencoded chunk. The only place this is really useful to you is in freeing. If you can overwrite a free list to have this situation where it fails, you can actually manipulate the size. With that size manipulation, you may be able to set up walls in free lists where they'll stop because you have manipulated the size. Again, just something to think about. It could lead to something more prosperous. Death of the bitmap flip. John McDonald and I actually used bitmap flipping in our exploit last year when we did our XP 2003 talk. Now this is kind of dead. Before, if you could trick a free list into thinking it was empty and you could alter the size, there was an XOR operation, right, that would flip the bit. That's not the case anymore. They use bitwise AND when allocating. That is, if you're allocating from a list, it can only become empty. Allocating from a list can never lead to that list becoming populated, right? The same with freeing. They use bitwise OR. A populated list after a chunk has been taken out cannot become more populated. With the encoding of the sizes and everything else, this isn't really useful to you anyway. Not to mention, dedicated free lists aren't on heap base anymore. So all in all, it did fix it, but at the same time, it's not as useful as it used to be. Sorry, Nico. I apologize. They ruined it for you. The last thing I kind of already talked about is safe linking. And to my knowledge, I think this directly addresses Brett Moore's paper, exploiting items on free list 0 in Windows XP Service Pack 2. You overwrite a B-link of an item on a free list. You insert a chunk before it. That address now points to the chunk you just freed. It's not the case. You get a heap log failure and a log what happened. The thing is, if the process doesn't terminate when the failure happens, you see that it just goes down, and it will actually update that list hint and put your chunk in. Well, since the chunk hasn't safely been linked in, you fully control the forward link and backlink of that value. So if you could get this to happen, you still have to deal with safe unlinking when getting this item back off the list, and that does terminate. But if not, and you can figure out something ingenious, you fully control the forward link and backlink in this scenario. All right, I think we're done with most of the boring stuff. Now we can get to tactics. The first tactic when addressing the low fragmentation heap is, how do I enable it for a certain size? I can guarantee you, if you make 18 consecutive allocations, the next allocation you will make will be in the low fragmentation heap. It will be coming from that user block. So this is pretty simple. You can do this in almost any application, i.e., create a bunch of DOM objects, in a network application, send a bunch of requests. It will turn it on. Unfortunately, a lot of times this isn't the case for all this stuff. You're going to get these user blocks that have been used, and there's going to be holes in them. The next offset isn't going to be nicely to the next adjacent chunk. It could be all over the place, really. This is where defragmentation comes in. You have to normalize this heap. A prerequisite for all the attacks that at least I have are chunks being adjacent to each other, directly adjacent. Now, be it that all the chunks in a user block, right, are adjacent because it's one big contiguous block of memory, but at the same time, you're going to want two things right close to each other. I talked to Alex Sotorov about kind of what he did when he was exploiting these things, and he was saying that making a large amount of allocations for the same size would actually fill these holes. And If these holes are filled, you have adjacent chunks. Not to mention, if you make enough allocations, you can completely exhaust a user block. And it won't quit using it. It will just allocate more memory for it. So you could potentially get a nice fresh user block for yourself after making a large amount of allocations. What do you do with this adjacent data? I think a great example of what to do with adjacent data as of recently was Peter Vuckenhill's, I hope I pronounced that correctly, but I don't think I did, paper that he did for Pwn2Own 2010. What he did is he overwrote a null terminator, right? And now that this null terminator was overwritten, the string was way longer than it was supposed to be, and he used it, in a process to exploit something. With adjacent data, you can overwrite chunk headers, and you can overwrite data inside of it. If you can get two C++ objects next to each other and write into the next one, that's going to be bad times for whoever wrote that application. Well, what if you can't afford to overwrite these things? What if the Munge C++ object is a few chunks away, and there's one used in between it? Well, you can actually use a series of allocations and frees based off the last in, first out structure of the low fragmentation heap. So you get these blocks. If you allocate a piece of memory, free it, allocate it directly again, you'll get the same address back each time for that given chunk. All right, so you have these chunks and you have adjacent data. What else can you do? Since you can get the same chunk back multiple times if you know the size and you kind of had a good idea of the allocation of a certain application. Data seeding. You can put data inside of chunks and have it stay there. If anyone went to Nico Weissman's talk yesterday, he gave you a very practical example of what you can do with the knowledge of data seeding and the sizes of allocations. Here in my example, I made 4 allocations. I wrote some memory to it. I freed all those 4 blocks. I made 4 subsequent allocations, this time not writing any memory. If you see, they generally have the same data inside of it. The only thing that's changed is the first 2 bytes, right? Because that's the free entry offset. And again, Nico talked in his presentation about using this, the free entry offset overwrite to overwrite a V table as well. So I think everyone should definitely check out his presentation, read his paper, buy him a beer downstairs. Okay, now it's time to talk about exploitation for all the busticati out there. The first thing I'll talk about is a technique that I call Ben Hawks number 1. Ben Hawks wrote a paper and did a Black Hat presentation in 2008. I've read it like 20 times, and there's literally like 30 techniques that he came up with in it. He just had a bunch of brilliant ideas. But I singled this one out because it just caught my eye. We saw when freeing a low fragmentation heap chunk, right, that if the unused bytes have a value of 5, more data is actually, the pointer is actually updated to a different location instead of the chunk header that you kind of just passed in there. Well, what could you do with this? You control the amount that is subtracted if you have an overwrite, and you control whether it gets triggered. I think the best thing that you could do with this is abuse C++ objects. So what you want to do, right, is you want to get 2 chunks adjacent to each other. One that you can overflow, one that you can overflow into. The one that you overflow into should be capable of being freed. If you overwrite those unused bytes to B5 and you overwrite the segment offset to a value control, you have 8 times 1 byte, so 8 times FF, negative range that you can point. Now it has to point to a valid heap entry, but if you're in the user blocks, every so often there are valid heap entries, especially if you make some allocations, there's going to be ones behind you. With this, you free that chunk. And since the last in, first out nature of the low fragmentation heap works, you make an allocation, you just got the address of, say, a C++ object that is currently in use. Overwrite whatever's there, especially the first 4 bytes. Hopefully that's a V table. Make a call to that C++ object. At that point, you can work on defeating dep, ASLR, whatever you want. Now for my half-assed version of an exploitation tactic. Before I talk about it, I wanted to explain to